Hello class! We're gonna do the odd homework problems for exam 3 for Cal 2. Let's sketch this thing. X equals 3t minus 3t squared, y equals 5 minus 5t squared. What do these graphs look like? X, when I ask when u equals 0, u equals 0 at 0 and at 1. 3t minus 3t squared equals 0. I get 3t, 1 minus t equals 0. So that equals 0 at 0 and 1. It's a parabola. It's going to have its vertex halfway between 0 and 1. If I plug in a half, I get 3 times a half is 3/4 is positive. So, yeah, this is what x of t looks like. What does y of t look like? 5 minus 5t squared, that's 5 times 1 minus t squared. It's 5, 1 minus t, 1 plus t. U equals 0 at 1 and at negative 1. Again, it's a parabola, has its vertex halfway in between, that's at 5. So y looks something like this. We're interested in the points -1, 0, 1 for y, 0, 1/2, 1 for x. I'd like to plot all those points on my graph if I want to understand what's happening. So it's -1, 0, 1, half, 1. X of -1 is 3 times -1 times 1 minus -1 is -6. Y at -1 is 0. At 0, x is 0, y is 5. At 1/2, x is 3/4, and y is 5 minus 5 times a half squared. That's 5 minus 5/4. That's 3 3/4. And at 1, our x value is 0, and our y value is 5 minus 5 is also 0. Okay, so I have some points of interest. Our x-axis needs to go out as far as -6. Our y-axis needs to go up as high as 5. Our graph is, our first plotted point is -6, 0. Prior to this point, y was negative and x was negative, so we're coming in from quadrant 3. I don't know what angle we're coming in at. I guess I can think about it. X is increasing, so we're coming in from the left. Y is increasing, so we're coming in from below. So, something like this direction. I don't know what angle, but it's an increasing function on this region. Then what's our next point? X is 0, y is 5. So we're going to come in from here to that point, between -1 and 0. X is increasing the whole time, y is increasing the whole time. At this point, y turns around and becomes negative. Okay. Our next relevant point is, so this is t equals 0. So this is the direction of the flow of time. When I get to t as a half, I'm at x equals 3/4, y is 3.75, so like around here. Something like that. And then our next relevant point is at t equals 1 when we get x equals 0, y equals 0. I'm going to turn around here, go through there, and then after that, x is negative, y is negative again. So something like this. Kind of looks like a parabola. I don't know if it's actually a parabola, but our shape is something like this. Okay. That was... oh, they didn't... oh, sketch. Check. Did the sketch. Now find dy dx and d squared y dx squared at the point 0, 0. Well, the point 0, 0 I've just worked out is the point when t equals 1. So that's the place where I need to find dy dx and d squared y dx squared. To find dy dx, it's going to be dy dt over dx dt. Derivative of the y function is negative 10t. Derivative of the x function is 3 minus 6t. So dy dx at t equals 1, which is the point 0, 0, will be negative 10 over 3 minus 6 is 10 thirds. Cool. To find d squared y over dx squared, that's the derivative with respect to t of dy dx over dx dt. Derivative with respect to t of dy dx is derivative of this is going to be quotient rule, I guess. Derivative of the top, leave the bottom alone, minus leave the top alone, derivative of the bottom over bottom squared, divided by dx dt is still 3 minus 6t. So I'm ending up with something over 3 minus 6t cubed, and the top is going to be negative 30 plus 60t minus 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 makes this negative 60t. Oh, these cancel. So it's just negative 30 on top? Yes, it is. Okay. I guess this I can factor the 3 out. 3 cubed is 27. And I'm left with 1 minus 2t inside there cubed. Can cancel by a 3. I get negative 10 over 9. 1 minus 2t cubed. So d squared y over dx squared at t equals 1 will be negative 10 over 9 times negative 1 cubed will be 10 over 9. That's this, that's this. They didn't ask for the Taylor. Wait, what are you doing? Should I save this? Something fishy's going on. 3 plus 3 minus 12 equals 0. No, it does not. Exam 3 homework odds. Cool. Find the total area enclosed by the x-axis and this curve. No, I didn't want you to go below, I wanted you to go above. Undo new page. Insert new page here. Nope. I gotta scroll down a little more and now say insert new page. There we go. Okay, the time frame we care about is from negative 1 to 1. So that's the part where that captures the part where it's enclosed by the x-axis. There's a good guess that the answer might be the integral from negative 1 to 1 of y dx, which in this case means y of t dx dt. But sometimes dx is negative and sometimes it's positive, and I need to think about what happens if I cut the thing into pieces and understand what's going on at those times. Here's t equals negative 1. Here's t equals 1. But we have this relevant point t equals 1/2, where dx dt switches between positive and negative. What do I get if I integrate from negative 1 to 1/2 y of t dx dt? That'll be the area between the x-axis and the curve is y, multiplying by dx dt, so this is positive, and this is positive. I will end up with this area positive. Okay, now what happens if I integrate from 1/2 to 1? Y of t, dx dt dt. That'll give me this region. Y is positive, dx dt is negative, because our x values are decreasing. So I'll end up with this area, but it counts as negative. So what I want is to add these two things together. I want this stuff to count as positive, and then I want this stuff that I didn't want there to count as negative. Adding those two together gives me the thing I want, good. And combining these two gives me the integral from -1 to 1. The part that I don't want gets cancelled out. The part that I do want is left behind. Perfect. The integral from -1 to 1 of y dx dt does the thing I want it to do. It very often does, but I feel like you need to check every time. Cool, so let's do that integral. The integral from -1 to 1 of what was y? Y was 5 minus 5t squared. Dx dt is 3 minus 6t dt. Let's FOIL that out. Yeah, I don't see any trick to avoid the foiling. 15 minus 30t minus 15t squared plus 30t cubed. Is this all right? Yeah, that seems right. Integrate that, you get 15t minus 15t squared minus 5t cubed plus, this one's not divisible by 4. I was hoping to get through this without fractions. 30 over 4 is 15 over 2 t to the 4th. Evaluate that from -1 to 1. Plug in 1. You get 15 minus 15 minus 5 plus 15 halves. Plug in -1. You get -15 minus 15 minus -5 plus 15 halves. Here I have positive 15 halves and negative 15 halves canceling. Here I have negative 15 minus negative 15 cancels. The other two are the ones that don't cancel, which is 10 minus negative 10 is 20. I'm getting the area is 20. Does this make sense? Our maximum, let's see, if I draw a rectangle around this thing, what size is the rectangle? We go up as high as 5. We go out as far left as, so 5 by, my rectangle would have a width of 5, or a height of 5 and a width of 6 3/4. So the area of that entire rectangle is like 30 something. And we are most of the rectangle, but not all of the rectangle. Getting an answer of 20 seems reasonable. Cool. Let's find the arc length of this curve. Arc length is the integral of the square root of dx dt squared plus dy dt squared. The bounds of integration are sometimes tricky. Here they just gave them to us. So this is the integral from 0 to pi of dx dt needs the product rule. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second squared. Plus dy dt is product rule. Derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. Here's hoping the thing inside the square root simplifies. Square that, I get sine squared t. Double the cross term is 2t cosine t sine t. Square the second term, t squared cosine squared t. Square this. Square the first part is cosine squared t. Double the cross term is negative 2t sine t cosine t. Square the last term is t squared sine squared t. Or close bracket to the 1/2 dt. What do we get? This thing cancels with this thing. That's a positive 2 and a negative 2 of the same thing. I have sine squared and cosine squared is 1. I have t squared cosine squared plus t squared sine squared. If I factor out the t squared, I'll get 1. So that'll be t squared. That's what's being raised to the 1/2 dt, integrated from 0 to pi. It's the graph of a hyperbola. I feel like maybe this is a geometry thing that we can just know. I guess I don't know anything about the area of a hyperbola. Never mind. I guess we do a trig substitution. Should be like t equals tangent theta. When I make my usual little doodle about remembering that trig identity that I never remember. Sine squared plus cosine squared is 1. So tangent squared plus 1 equals secant squared. Cool, yeah, I want tangent. Let's let t equal tangent theta. dt will be secant squared theta d theta. Gross. When t is 0, theta is 0. When t is pi, what is tangent pi? Wait, no. I want tangent theta to be pi. Wait, really? T is pi, so theta is tangent inverse pi. Weird. That's weird, right? Yep, that's weird. I guess the thing that's weird is all the trig left our integral. Back over here, when I was integrating sine and cosine from 0 to pi, that made sense, but after a lot of work, the sines and the cosines left, and now I'm integrating a thing that doesn't have any trig in it from 0 to pi. It's weird. Is why this weird thing is happening. Okay. Square root of 1 plus tangent squared is square root of secant squared is secant. dt is secant squared theta. We're integrating secant cubed. This integral's the one that's a pain. Do I just look it up? Do I do it? Let's do it. We're going to do parts. U is secant squared. dv is secant theta. So du, wait, no, I want dv to be the one I can integrate. I want dv to be the secant squared. So du is derivative of secant as secant theta tangent theta. V is the integral of secant squared as tangent theta. I get that this equals uv, secant theta tangent theta, evaluated from 0 to tangent inverse pi. Oh, I wrote tangent inverse theta, that should have been tangent inverse pi. Minus the integral of v du is tangent theta, secant theta tangent theta. That's secant theta tangent squared theta. Tangent squared becomes secant squared minus 1. So replace tangent squared with secant squared, I get secant cubed. Replace it with minus 1, I get minus secant theta. Plug in 0, you get 0. Plug in tangent inverse pi, you get secant tangent inverse pi. I want the angle whose tangent is pi, so opposite over adjacent should be pi over 1, so this will be square root of pi squared plus 1, so secant is 1 over cosine. Cosine is adjacent over hypotenuse is 1 over square root pi squared plus 1, so secant is just root pi squared plus 1. I'm getting pi root pi squared plus 1 minus this. I'm getting that the integral from 0 to tangent inverse pi secant cubed theta equals pi root pi squared plus 1 minus the integral from 0 to tangent inverse pi secant cubed theta minus negative integral 0 to tangent inverse pi secant theta. Move this to the other side. I get 2 copies of the integral that I want. Equals pi root pi squared plus 1 plus the integral of secant. The integral of secant is natural log absolute value secant theta plus tangent theta. And I need to evaluate that from 0 to pi. So the integral I want from 0 to tangent inverse pi is going to be half pi root pi squared plus 1 plus, I need to plug in 0. When I plug in 0, I get 1, natural log 1 is 0. Okay, so the 0 part does go away here. Natural log of 1 plus 0 is natural log 1 is 0. Yeah, that's nothing. So I just need to plug in pi. Secant, not pi, tangent inverse pi. Tangent inverse pi is pi. Secant tangent inverse pi we just worked out is root pi squared plus 1. So there's our answer. Gross. Okay. Sketch these polar curves. Try and do the first 2 by hand. Use a grapher on all 3 afterwards. What does cosine 6 theta look like on a regular graph? It looks like cosine theta, but it's oscillating twice as fast. While a regular cosine between 0 and 2 pi will go down and up once, cosine 6 theta will do that 6 times. So I guess I want to cut this into 6 equal pieces. I guess I want to cut each of these intervals into 6 pieces. Let's go into thirds. Pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then similar deals here. So now we've cut the interval into 12 chunks. We need to go down and up for every 2 chunks. So down, up, down, up, down, up, down, up, down, up, down, up. I did that last one wrong. Should be at the bottom here, top here, something like that. So when I try and do this polarly, I need to think in pi over, so let's just cut it into the pi over 6s that I did this by. So dupe, 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 dupe. At 0 we get 1. By the time we get to pi over 6 we need to be at -1. Halfway between there we should be at 0. So like boom, boom is our first arc. Now between here and here we need to go from -1 back up to 1. So doop, doop. Back down to -1. Doop, doop. Back up to +1. Doop, doop. Back down to -1. Doop. Back up to +1. That's from 0 to pi. We didn't land where we started, so we're not going to now repeat the same thing again. So now we're going to fill in the other half of the flower. From +1 down to -1 here, which will put us at that point. To +1 will put us at that point. To -1 will put us at that point. To +1 will put us here. To -1 will put us here. To +1 will put us here. I've got these petals overlapping each other. They shouldn't be overlapping each other. But, you know, I'm doing my best. Cool. So this is basically what r equals cosine 6 theta should look like. Let's try r equals sine 4 pi over 3. 4 theta over 3. What do you look like in a regular graph? 2 pi might not be enough to catch the whole thing. When you add fractions in, like, cosine 6 theta is definitely going to repeat itself every 2 pi because it'll have repeated itself 6 times. When I plug in 2 pi to 4 pi over 3, I get 8 pi over 3. We're not back at the start. We are ready to go again. So, this is going to be rough. I might need to go out to 6 pi to catch an entire before it starts repeating itself. Looks like we're back. Sorry about that. So I'm thinking about when do we take sine of 2 pi? I know that sine goes through one branch when the input goes from 0 to 2 pi. I know that I'm thinking about sine 0 at 0, trying to figure out where is it that I'm going to hit the end of my first repetition of a cycle of sine. That'll be when I'm trying to plug 2 pi into sine. That'll be when 4 theta over 3 equals 2 pi. I solve that, I get theta is 3 pi over 2, pi and a half. So here to here will be one branch of sine. So from here to here should be up, down, down, up. So it's going to be every 3/4 of pi is when we go up to down. So 1/2 and 1/4 will put us here and then here. Here's going to be the end of my next repetition, here and then here. And then here's going to be the end of my next repetition, here and then here. If I take the 2 pi interval and repeat it 3 times, I'm going to get 4 cycles of sine. Something like this. Okay. Let's try graphing this. 0, pi over 2, pi, 3 pi over 2. We start out at 0. We're going to increase and equal 1 when we are at 1/2 of 3 pi over 2. That's at 3 pi over 4. That's here. So this needs to go around and get its biggest at this spot. And then it needs to come down and equal 0 halfway between pi over 2 and pi. Wait, no. Wait, why do I have 3 pi over 4 to the left of pi over 2? Something went wrong here. This is 3 pi over 4. This should be 3 pi over 8 is the place where it gets its biggest. So, almost pi over 2, but not quite. Here's pi over 4. 3 pi over 8 would be halfway between these two angles, is here. This is where the thing should get up to 1. Okay. Don't crash. Okay, so this, where we equal 0 again, is 3 pi over 4. This place where we equal 1 is 3 pi over 8. I get a chance to start over. Here's my circle of radius 1. At theta equals 0, we start at 0. We're going to go up to 1 at 3 pi over 8, which is 3/4 of the way to pi over 2. Here's pi over 4. Here's 3 pi over 8. That's where our thing is going to equal 1. So we need to go from 0 up to 1 in that angle span. Now we're going to go back to 0 at 3 pi over 4. So here's the place where we come back down to 0. After this, we're negative. We're going to reach our bottom, our negative 1, 1/8 of a turn after pi. So here is where we will hit negative 1, which will put us at this point. So now from here I need to do a similar loop here. And then come back to 0 at pi and a half. So like that. Now I'm back in the positives. Weird. So I guess I'm copying this loop in rotation forever. We're going to here, to there. Yeah. And then to here. Coming at it horizontally now. And then to here, coming out of it horizontally, going back and facing that. And then to here. Coming in vertically. And then to here. Coming in from this angle. And then to here. Coming in from this angle. Are we back where we started? Oh, this should have been coming in horizontally instead, and now we're back where we started. Something like that. These ones are supposed to overlap each other. So this is another... The last one was a 12-petal flower where the petals don't overlap. This one is a 8-petal flower where the petals do overlap. Cool. I guess the problem says use a grapher. Let's do that. Dear Desmos. I want R equals, first one was cosine 6 theta. Where's a close bracket? Close bracket. Nope. Settings here. I know I just looked this up. Okay. turning my laptop inside out. How do you do a polar graph in Desmos? Yeah, how did you... Well, whatever, I can just use this one. Oh, do you click here? No. Okay, give me r equals cosine of 6 theta. Cool. Pretty well nailed that. What's this one? Sine 4 pi over 3? Sine of 4 theta over 3. Ooh. Ooh. Cool. Something like this. Can I overlap it and see how? Not bad. Alright, and this last one, sine cubed 2.5 theta. Let's try this. So that'll be sine of 2.5 theta cubed plus cosine 2.5 theta cubed. Oh, I love it. I love it so much. I think we're alternating between, so we're following one of these up, then we do a weird little wavy thing, and then we follow the next one down. So let's just go from theta equals 0 to 1. Okay, we start with a wavy thing. I just love this graph. Neat. I wouldn't want to try and graph this on my own. And the fact that it's like tangent to itself all over the place, that's my favorite part. Graphing stuff in Polar is so fun. Like, seriously, I know it's like a homework thing, but sit down and try and come up with a goofy, there's just a million crazy, cool graphs you can make in Polar. Okay, what do we got next? I got a bunch of things that are written in Cartesian that I want to convert to Polar. This one I'm going to multiply both sides by r. R squared equals 5r. Cosine theta, that becomes x squared plus y squared equals 5x. Check. I could solve for y if I wanted to. Theta equals pi over 6. Well, if I take tangent of both sides, tangent theta equals tangent pi over 6. That says y over x equals, what is tangent pi over 6? That's a half over root 3 over 2, so that's 1 over root 3. So y equals root 3 over 3x. R equals 4. X squared plus y squared equals 4 squared is 16. I guess I'm squaring both sides. Ooh, this one's gross. R squared sine 2 theta equals 1. I guess I'd rather use a trig double angle identity to split up the sine 2 theta. That's r squared times 2 sine theta cosine theta equals 1. So I get 2. Let's divide both sides by 2. I get r sine theta, r cosine theta equals 1/2. Now I have an x and a y. xy equals 1/2. This one uses the other double angle, so I get r squared. What's cosine 2 theta? It's cosine squared theta minus sine squared theta, right? So I get r squared cosine squared theta minus r squared sine squared theta equals 1. So this is x squared minus y squared equals 1. Oh, hey. Huh. Okay, this is cute. X squared minus y squared, this is a hyperbola. In the traditional conic section chapter of your pre-cal textbook, hyperbola. This is a graph that people always told you was a hyperbola. So that's this type of hyperbola. And this is this type of hyperbola. And I know that if you switch a sine and a cosine, you're not really changing the graph, you're just rotating it. So this feels to me like a confirmation that this type of hyperbola that you did in pre-cal matches this type of hyperbola that you talked about in pre-cal but didn't rotate this graph, and you really do change it from this to this. It might be this type instead of that type. I don't remember what the major axis, minor axis stuff was. That's a little thing that always bugged me from pre-cal, that they told me this is a hyperbola, but we only ever did hyperbolas like this or like this. But here's a little confirmation that they're the same. Cute. Cute, cute. Let's find the equation of the tangent line to r equals cosine theta over 3 at theta equals pi. This is the one, there's a formula you could try to memorize, but I wouldn't bother. I would just use that y equals r sine theta, x equals r cosine theta, and then just use the regular parametric definition of a derivative. I'm going to need the points, and I'm going to need the tangent line. Y is r sine theta becomes y of theta is, what was r? It was cosine theta over 3 sine theta. X of theta is cosine theta over 3 cosine theta. To find dy dx, it's going to be dy d theta over dx d theta. What's dy d theta? I need the product rule. Derivative of the first, negative cosine theta over 3 times 1/3. Leave the second alone, sine theta. Plus leave the first alone. Oh, wait, derivative of the first is negative sine, not negative cosine. Okay, plus leave the first alone, cosine theta over 3. Derivative of sine is cosine theta. Over derivative of x with respect to theta. Derivative of the first is negative sine theta over 3. Leave the second part alone. Oh, times the 1/3. Leave the cosine theta alone. Plus leave the first alone. Derivative of the second is cosine theta over 3. Derivative of cosine is minus sine theta. So dy dx at theta equals pi. Can I do all these trig functions in my head? I need negative. What is sine pi over 3? Pi over 3 is here. Its sine is root 3 over 2. Its cosine is a half. So root 3 over 2 times 1/3 times sine pi is 0. Cosine pi over 3 is a half. Cosine pi is negative 1. Negative sine pi over 3 is root 3 over 2 times 1/3. Cosine pi is negative 1. Cosine pi over 3 is a half. Sine pi is 0. So that part and that part go away. And I'm left with negative a half over negative negative is positive root 3 over 6. So I get negative 3 over root, this is root 3. Negative 1/2, 6 over root 3. Your 3 over root 3 is, yeah, negative root 3 is our slope. What's y of pi? Y of pi is 0. What's x of pi? X of pi is, I'm looking at these formulas, by the way. X of pi is cosine pi over 3 is a half. Cosine pi is negative 1 is negative a half. So our tangent line should be y equals y value plus slope x minus x value. So this is going to be y equals, our y value is 0, Our slope is negative root 3. X minus our x value is negative a half. I should get this. Let's try this out. I got my grapher open. Do you actually look like a tangent line? It's cosine. Oh, I should use this keyboard probably. Cosine of theta over 3. Dang it. Why did you get rid of the polarness? It stopped being polar. Let's just delete that part instead. Watching me try and figure out how to type without turning my keyboard inside out is not the best video, I think. Okay, I didn't want 2.5 theta, I wanted theta over 3. So just delete that part, go over here, put in over 3. Okay, allegedly the tangent line to this is y equals what's it supposed to be? Y equals negative root 3 x plus a half. Negative root 3. Nope, I want to be outside the root. X plus a half. Hey, yep, sure enough, tangent. Cool. It's only tangent to one of them because they specified theta equals pi. Theta equals pi will be the first time we cross over there. So, cool. Looks like it is an actual tangent line. It worked. Find the total area inside the curve r equals sine 3 theta. What does r equals sine 3 theta look like? Sine theta would normally go up and down once. Sine 3 theta will do that 3 times. So two pi over 3 we will have done. Nope, we need to go up and down. So pi over 3 is where we'll hit 0. Zoop, zoop. Zoop, zoop. Zoop, zoop. This should be what sine 3 theta looks like. What does that look like in a graph? We start at 0, so our graph starts here. We will go up to 1 at pi over 6, that is here. And then back, so over the course of this angle, we will go up to 1 and back to 0. So you. Then over the course of this chunk, we will go down to negative 1 and then back up to 0. Shoot, shoot. Then over the course of this chunk, we will go up to positive 1 and back down to 0. And then over this chunk, we will go up to 1 and back to 0. So we are repeating ourselves. Are we definitely repeating ourselves? The fact that we're repeating ourselves is the fact that this chunk is the same as this chunk but with a minus sign. It's the fact that r equals sine of, when I replace theta with theta plus pi, I'm getting negative the original. Does this identity actually hold? I'm hoping that sine of 3 theta plus 3 pi do u equal negative sine 3 theta. If you know a cofunction identity, you can probably do this right away. Otherwise, I guess I'm probably using angle addition on this. Sine this, cosine that, plus sine that, cosine this. Do u equal sine 3, negative sine 3 theta. Sine 3 pi is 0. Cosine 3 pi, pi 2 pi 3 pi is negative 1. Yeah, check. I get negative 1 sine 3 pi theta. So you are back where you started from. This identity thing is me confirming what the picture looks like, that you will be doing the exact same thing again. I guess the thing that's going on that makes me feel confident is when I got to, so we did this branch here, then we did this branch was here, and then this part was here, was this purple part. So the thing I'm banking on is that this shape is the exact same as this shape, but upside down, which it is, because I know how sine works. Okay, I need the total area inside the curve. The thing I've learned from learning that it repeats itself is I should go from theta equals 0 to pi. Don't go to 2 pi. 2 pi will count everything twice. Or I could go from 0 to pi over 3 to get one petal, and then triple that. The calculus books always do that. They always say, I'm going to find the area of one petal, and then multiply that by 3. I don't know, pi is an easier number to plug in than pi over 3, so I don't see the value in that. I want the integral from 0 to pi of 1/2 r squared. To get the area inside a polar thing, you're integrating 1/2 r squared. R squared is sine squared 3 theta. That's 1/2 integral 0 to pi of 1 minus cosine double that over 2. So I get 1/4. I'm integrating, so I'm pulling the 1/2 out again. Now I'm just integrating 1 as theta. Integral of cosine 6 theta is sine 6 theta over 6. I need to evaluate that from 0 to pi. Plug in pi, you get 1/4 of pi minus 0 minus 0 minus 0. I'm getting pi over 4. Which should mean these petals fill up a quarter of the circle. Yeah, I guess that makes sense. I guess it's filling up half of this wedge. Yeah, I can buy that. Find the total arc length of r equals cosine to the 4th theta over 2. Yuck. I don't really want to try and sketch this thing. This seems rough to sketch. Good news is cosine to the 4th is positive. Which means that whatever it's doing here is going to be some positive thing. When we come around to here, it can't overlap itself because it's going to be doing something positive here. The graph can't overlap itself, and I don't need to worry about, like for the last example, I needed to know that the graph is repeating itself, so I should integrate from 0 to pi, not from 0 to 2 pi. This graph is definitely not repeating itself. Will it repeat itself when I get to 2 pi? Oh, I guess maybe I do need to. The fact that there's a cosine always repeats itself after 2 pi. Cosine theta over 2 needs to wait until... gross. I guess I do need to think about the graph of this. Okay, let's think about... What does cosine do from 0 to 2 pi? It goes from 1 down to negative 1, back up to positive 1. If you square it or raise it to the 4th, the key thing is that when you go down to 0, you don't pass 0, you come back and are positive again. So our cosine to the 4th should look something like this. It's probably going to like jump down and be like really low, because when you take a fraction and raise it to the 4th, it gets smaller again. But that would be cosine to the 4th of theta. Cosine to the 4th of theta over 2 will do the same thing, but it'll take half as long. Okay. It looks like it's going to repeat itself from 0 to pi. Yep. Okay. So 0 to 2 pi will be enough to catch the whole thing. Because by raising it to the 4th, you're causing it to repeat itself twice as often, so the theta over 2 is canceling the... Cool. So I want to go from 0 to pi, is the thing I'm convincing myself of with this picture. The part that it does from 0 to 2 pi is the same that it's going to do from 2 pi to 4 pi. So I want to integrate 0 to 2 pi, the square root of... It's worth knowing the arc length formula for polar. It's r squared plus dr d theta squared. Why is it this and not derivative of x squared plus derivative of y squared? It simplifies to this. It's a crazy simplification, similar to the one we had a second ago. Cool. What's r squared? Is this a really hard integral? R squared is cosine to the 8th theta over 2. dr d theta is 4 cosine cubed theta over 2 times negative sine theta over 2 times a half. And that all needs to get squared. Okay. So I'm integrating 0 to pi. Cosine to the 8th theta over 2 plus 4 times a half is 2, squared is 4. The negative goes away because it's being squared. Cosine cubed squared is cosine to the 6th theta over 2. Sine squared theta over 2. This has got to be rigged up so this integral's not that bad. Okay, factor out a cosine to the 6. The 4, why is that 4 there? I wish that 4 wasn't there. Well, I get cosine to the 6th theta over 2 times cosine squared theta over 2 plus 4 sine squared theta over 2 I can pull the cosine to the 6 out. I'll be left with a cosine cubed theta over 2. Oh, it's in absolute values. Cosine squared plus sine squared becomes 1. Should I pull out that 1? 1 plus 3 sine squared theta over 2? Is cosine always positive between 0 and pi? Theta over 2 says this is between 0 and pi over 2, really. Yes, cosine is positive there. So the absolute values don't actually matter. Wait, I'm not supposed to be going 0 to pi, am I? I'm supposed to go 0 to 2 pi. So I do need those absolute values. I probably just need to go 0 to pi and double it. I guess that's the reason you do the... say we're only going to talk about one leaf, so you don't have to think about positives and negatives. That's not an issue for area, but it is for arc length. What the... how do you do this integral? Okay, step 1, let's deal with the absolute values. There's going to be some kind of symmetry here, right? Whatever you're doing from 0 to 1/2, you're going to do the same thing but backwards from here. So we're going to go from positive to 0, from 1 down to 0 at pi over 2. And then you're going to go from that back up to 1 in a symmetrical way. Whatever the arc length is here, it's going to be the same arc length here. So instead of going from 0 to... Oh, this is after a bunch of reduction. Okay, whatever the arc length is here, it's the same thing here. So it's okay to go from 0 to pi and double it. That lets me get rid of these absolute values, because now cosine is positive on that region. I guess I'm going to try the u substitution. U equals 1 plus 3 sine squared theta. I get du is 6 sine theta over 2 cosine theta over 2 1/2. Is this any good? I can soak up one of the cosines. The cosine squared can turn into a sine squared, can turn into a u. I'm just left needing an extra sign that I don't get from anywhere. Man, I don't see how to integrate this. Am I missing something? R squared is cosine to the 8. dr d theta is 4 cosine cubed sine. 4 times 1/2 is 2. Squared makes it 4 again. Should I be doing like a trig substitution on this trig integral? Maybe just use u equals sine theta. Yeah, let's just try a much simpler substitution. Let's just try and get all the trig stuff out of here and see what we're looking at. Alright, we're going to try u equals sine theta over 2. du is going to be 1/2 cosine theta over 2. Bounds of integration change. When theta is 0, u is 0. When theta is pi, sine pi over 2 is 1. So now we're integrating 0 to 1. One of these cosines, I wish I had a 1/2. I'll stick an extra 2 out there to account for that. One of those cosines becomes part of the du. I'm left with a cosine squared. I'm going to do the messy in-between step where some of my things don't change. How do I change this cosine squared to be in terms of u? Well, sine squared is u squared. This is 1 minus sine squared, so this is 1 minus u squared. How do I integrate that? Probably with a trig substitution. I want root 3u to be tangent theta. Don't use theta, let's use alpha. So root 3 du becomes secant squared alpha d alpha. I wish I had a root 3 here. One minus u squared becomes 1 minus tangent squared alpha over 3. Root 1 plus 3u squared becomes root 1 plus tangent squared becomes secant alpha Root 3 du becomes secant squared alpha d alpha, and I need to change d alpha. It's really hard not to write theta. Okay, and my new bounds of integration are when u is 0, alpha is 0. When u is 1, that's when tangent alpha is root 3. I think that's one of the ones we know. I want y over x, 1/2 root 3 over 2. Yeah, so tangent is root 3 at pi over 3. Alpha equals 0 to pi over 3. Okay, not so bad. I always insert the new page on the wrong spot. I got 4 over root 3, integrating 0 to pi over 3. This is secant cubed alpha minus 1/3 tangent squared secant cubed Okay, and now you integrate this. And we're back to integrating secant cubed again. We're also integrating secant cubed tangent squared, which is also a very bad integral. Okay, so I got 4 over root 3, integral 0 to pi over 3, secant cubed alpha d alpha. I'm just going to look up the integral of secant cubed in a second, because we did it just on the last page. Minus 4 over 3 root 3, integral from 0 to pi over 3 of tangent squared secant cubed. How do you integrate tangent squared secant cubed? You want to split it into parts and then turn it back into the same problem that you've already done. It's the same fundamental trick that you do for secant squared or any of them. I want to let u equal tangent squared alpha secant alpha, I guess, and dv to be a thing I can integrate as secant squared alpha. Like I'm pulling off a secant squared to be the dv because I know the integral of that. V will be tangent alpha. Du will be derivative of this, needs the product rule. 2 tangent alpha secant alpha plus tangent squared derivative of secant. Derivative of secant is secant tangent, so secant alpha tangent cubed alpha. So I get minus 4 over 3 root 3. uv is tangent cubed secant. I need to evaluate that from 0 to pi over 3. Minus, cancels with the minus 4 over 3 root 3 that was already out front. Integral from 0 to pi over 3 of v du is, multiply the tangent on there, I get 2 tangent squared secant alpha. Plus, multiply the tangent on here, secant alpha tangent to the 4th alpha, d alpha. Alright, tangent squared secant can turn into secant cubed, which I can lump in with the first integral. Secant alpha tangent to the 4th alpha. Okay. Can I do this real quick? How hard is this to do? What is tangent pi over 3? Tangent pi over 3 is root 3. What is secant pi over 3? Cosine pi over 3 is 1/2, so that's 2. Plug in 0, tangent 0 is 0, so that goes away. So So this isn't that bad to do. I get 2 root 3 cubed. Root 3 cubed is 3 root 3. Cancels with that 3 root 3. So I get minus 8. That's just 2 times 4 is minus 8. Okay, that's not too bad. Plus 4 over 3 root 3. Integral 0 to pi over 3. 2 tangent squared. I want to turn into a secant squared. Tangent squared plus 1 equals secant squared. So that becomes 2 secant squared minus 1 secant. Okay, plus 4 over 3 root 3, integral 0 to pi over 3, secant alpha tangent to the 4th. I want to turn 2 of those secants and 2 of those tangents into 2 secants. Tangent squared is secant squared minus 1. Okay. So, pull the negative 8 out front. 4 over root 3, integral 0 to pi over 3, secant cubed theta, secant cubed alpha d alpha. Where half this time is spent changing thetas into alphas. Plus 4 over 3 root 3, integral 0 to pi over 3, 2 secant cubed. These two things are like terms I can combine. Minus 2 secant. Yeah, so that will be 8 over 3 root 3. Integral of secant alpha. That one's not too bad. Plus 4 over 3 root 3, integral 0 to pi over 3. I don't... this is too gross. I'm hitting a roadblock because this is going to give me the original integral I want again, secant cubed alpha tangent squared alpha. But I didn't keep a clean enough thing on the other side. Like, I want to move to the other side of the and say, okay, now I have this many of the original problem. But my original problem had other junk in it too. This is... is there a way to clean this up quickly? This is rough. Our last integral is going to be minus 4 over 3 root 3, integral 0 to pi over 3, secant tangent squared. Which again I can turn into a secant cubed. Okay, I said I would do the odd problems. I guess I gotta suck it up and do this. Let's give this thing a name. I'm gonna call this capital A for the answer. I'm gonna let A be the answer that we want. I'm gonna write I is the integral 0 to pi over 3 secant cubed alpha, which I'm going to look up in a second. I'm going to let j be the integral from 0 to pi over 3 tangent squared alpha secant cubed alpha. So this line tells me that a equals I minus 1/3 j is the thing that we want. This is going to all turn into i's and j's in a second. So a equals I minus 1/3 j also equals -8 plus 4... I'll put a 3 on bottom and top here. So you're 12 over 3 root 3 plus 4 over 3 root 3 makes... Actually, let's hold off until we've gotten everything. I've still got more secant cubed integrals to clear up in a second. Well, no, let's mush those together now. -8 plus 16 over 3 root 3 integral 0 to pi over 3 secant cubed theta. Secant cubed alpha d alpha. Minus 8 over 3 root 3 integral 0 to pi over 3 secant alpha d alpha. Plus 4 over 3 root 3. The whole point was to clean this up by changing these to letters. The integral from 0 to pi over 3 secant cubed alpha was I. Integral of secant alpha we'll do ourselves in a second. Plus 4 over 3 root 3 integral secant cubed tangent squared is j. Minus 4 over 3 root 3 integral 0 to pi over 3 secant alpha tangent squared is secant alpha. Tangent squared becomes secant squared minus 1. D alpha, not theta. So this becomes minus 4 over 3 root 3 secant cubed is I plus 4 over 3 root 3 integral secant alpha. Does this happen to cancel that? It does not. -8 over 3 root 3 integral 0 to pi over 3 secant alpha plus 4 over 3 root 3. So this combines with this becoming a minus 4 instead of a minus 8. So we get equals -8 plus 16 over 3 root 3 I plus 4 over 3 root 3 j minus 4 over 3 root 3 I smushes with that 16 to become 12 over 3 root 3, which is 4 over root 3. So I did this and this combined to make that. Yeah, and I'm left with minus 4 over 3 root 3 integral 0 to pi over 3 secant alpha. Let's do that integral now. The integral of secant alpha is natural log absolute value secant plus tangent. I need to evaluate that from 0 to pi over 3. At 0, we get secant 0 plus tangent 0 is 1, natural log 1 is 0. Great, goes away at 0. Plug in pi over 3. Okay, new page. Is there really no root 3 here? Where did the root 3s show up? Yeah, there should have been a 4 over root 3 on this line. A isn't I minus 1/3 j. A is 4 over root 3 I minus 1/3 j. Okay, minus 4 over 3 root 3, plug in pi over 3, plugging in 0 gives you 0, yeah, so I just need to plug in pi over 3. Secant pi over 3, cosine is a half, so secant is 2, tangent pi over 3 is root 3. Absolute value of that is positive. So, this is now an equation we can solve for j in terms of I. 4 over root 3I minus 4 over 3 root 3j equals negative 8 plus 4 over root 3I plus 4 over 3 root 3j minus 4 over 3 root 3 natural log of 2 plus root 3. Move this to the other side. I guess these i's cancel if I'm solving for j now. I get negative 8 over 3 root 3 j equals negative 8 minus 4 over 3 root 3 ln 2 plus root 3. Oh, I'm actually solving for j not in terms of I. I'm just getting what that integral is. Cool. J is going to equal, multiply by 3 root 3 divided by negative 8, 3 root 3, minus the negative cancels, plus 1/2, natural log 2 plus root 3. We have what J is. We just need what I is. I am going to look up, because we already integrated secant cubed once today. What was I? I was the integral from 0 to pi over 3 of secant cubed. Yeah. Integral of secant cubed. This integral has its own Wikipedia entry. It's half secant tangent plus half natural log absolute value secant plus tangent. I need to evaluate that from 0 to pi over 3. Plug in 0, you get 0 here, 0 here. Okay, so the 0 goes away. I just need to plug in pi over 3. Secant pi over 3 is 2, tangent pi over 3 is root 3. Secant pi over 3 is 2, tangent pi over 3 is root 3. So I get root 3 plus half natural log 2 plus root 3. So our answer is 4 over root 3 I minus 1/3 j. So it's 4 over root 3 times I, which I just said was this. So 4 over root 3 times root 3 is 4. Plus 4 over root 3 times a half is 2 over root 3 ln 2 plus root 3. minus 4 over 3 root 3j. That times 4 over 3 root 3 will be 4. So those parts cancel. Minus 4 over 3 root 3 of this is 4 over... Am I getting 0? Oh, it can't be 0. Minus 4 over 3 root 3 times 1/2 ln 2 plus root 3. Yep, that's 0. I don't think the arc length is 0. Oh. I think this is the right way to do it. You know, if this stream's going to be useful, I need to stop doing this problem. I'm going to move on to the next one and try and finish this problem before I post the solutions. I got vertices of 0, 0, 3, 0, 4, 1. I'm revolving around the x-axis. Use the shell method and the disk washer method. A triangle. That sounds way easier. 0, 0, 3, 0, 4, 1. Get this goofy obtuse triangle, and we're revolving it around the x-axis. I want to use both the shell method and the disk washer method. One of those is going to have a horizontal line segment. The other one is going to think about a vertical line segment. Let's start with thinking about a horizontal line segment. Let's draw this purple horizontal line segment. I guess I probably want equations of all these lines. This line has a slope of 1/4. This is y equals 1/4 x. This line has a slope of 1, and it would have a y-intercept at -3, so this is y equals -3 plus 3x. If I'm thinking about a horizontal segment and revolving that around the x-axis, this is going to be the shell method. It's going to be an integral with respect to y, because I need to to move that line segment up and down. I'm changing the y value. The y values are ranging from 0 to 1. I want 2 pi r times h. My r value is y. The distance between y and 0 is y. Our h is the gap from here to here. I need to subtract the x coordinates to get horizontal distance. So this x equals 4y, and this x equals y plus 3 over 3. So right minus left is y plus 3 over 3 minus 4y dy. This is our integral. Oh, this is an integral I can totally do. Let's factor out the 2. Let's also factor out a 1/3. Let's factor out 2/3 pi. The 2's out, the pi is out, I'm left with y. I'm multiplying this by 3 when I factor out a 1/3. I get y plus 3 minus 12y. This is integral. This is 2 pi over 3, integral 0 to 1. Y minus 12y is negative 11y, so I get negative 11y squared plus 3y dy. It's 2 pi over 3. The integral of that is negative 11/3 y cubed plus 3/2 y squared. Evaluate that from 0 to 1. Plug in 0, you get 0. Just got to plug in 1. 2 pi over 3 times 3/2 minus 11/3. I guess I want a common denominator. Common denominator inside here will be 6. You're 22 over 6. You are 9 over 6. 9 minus 22. Uh-oh. I'm getting a negative number. Volume shouldn't be negative. This stuff's all positive. Is y plus 3 over 3 not bigger than 4y? Did I solve that equation wrong? The slope is 1. Y plus 3. Something's wrong. When I plug in y equals 1, I'm not getting x equals 4. Oh, the slope is 1, not 3. I shouldn't have put a 3 here. Y equals just negative 3 plus x. Okay. So x is just y plus 3. This is way simpler. I usually would rewrite my mistakes in red, but I want this to be legible for someone just reading the PDF later, so I'm not going to do that here. That's just 3 minus 11y, right? Nope, no 12. No factoring out a third. I'm just going to factor out a 2 pi. Your y plus 3 minus 4y is just 3 minus 3y. Okay. 2 pi, integral 0 to 1, 3y minus 3y squared. 2 pi, the integral of that is 3 halves y squared minus y cubed, evaluated from 0 to 1. Plug in 0, you get 0, just got to plug in 1. Plug in 1, you get 3 halves minus 1 is a half. You get pi. Cool. Now let's do it with disk washer. Disk washer is going to be annoying because we got a phase shift. You're supposed to spell disk washer with a K, not a C. So this time we're doing a vertical strip. Our vertical strip goes up as far as y equals 1/4 x, and down as far as the x-axis if x is less than 3, or it goes up as far as 1/4 x and down as low as negative 3 plus x if x is between 3 and 4. Because it does a different behavior before and after 3, we're going to have to split the integral up. I would think of the integral of 0 to 4 of big R squared minus little r squared. But this thing shifts at 3. I mean, I could make a piecewise defined function or something, but that's not any easier to integrate. So it's going to be pi integral 0 to 3 plus pi integral 3 to 4. Between 0 and 3, we're integrating top function squared, 1/4 x squared minus 0 squared. Between 3 and 4, we're integrating 1/4 x squared minus bottom function is negative 3 plus x squared. So I got pi over 16 integral 0 to 3 x squared. This one is going to be pi integral 3 to 4 x squared over 16 minus, FOIL that out, I got x squared minus 6x, but it's plus because of that minus, plus 9, but it's minus because of that minus. X squared over 16 minus x squared is going to be negative 15 over 16 x squared. I got pi over 16, x 1/3 x cubed needs to get evaluated from 0 to 3. Integral of that, x cubed divided by 3, negative 5 over 16 x cubed, plus 3x squared, minus 9x. Evaluate that from 3 to 4. Gross. This is supposed to end up being pi. I get, plug in 3, 27 over 3 is 9 pi over 16. Plug in 0, you get 0. Plus pi times. Plug in 4, 4 cubed, well it's 4 times 4 times 4, but dividing by 16 gives me negative 20. One of the 4's is left, times 5 is 20. Plus 3 times 4 squared is 16. Times 3 is 48. Minus 9 times 4 is 36. Minus, now plug in 3. 3 cubed is 27 times 5 is negative, I can do 5 times 27, it's 135, 135 over 16. Plug in 3, you get 27, plug in 3, you get 27. Okay. Uh, 28 minus 36. Well, 48 minus 36 is 12, plus negative 20 is negative 8, plus 135 over 16. What's 8 times 16 is 128. This is 7 over 16. I get 16 pi over 16. Is pi. Is the same as the other answer. Is a good feeling. If you don't get the same answer, don't freak out over it. You probably just added the fractions wrong. Don't stop taking the test. Move on to the rest of it. The region bounded between y equals sine x and y equals 0. Between 0 and pi, so this is one hump of sine, is being revolved about the line x equals negative 1. That's a vertical line over here. I want to set this volume up for both shell and washer, but I only want to compute one. That probably means one of these is super hard. You know what, I just did a hard problem. I'm going to take a drink of coffee. Okay. For, what is this function? This is y equals sine x. One of them is going to be a vertical line segment, one of them is going to be a horizontal line segment. I think the shell method is going to be the easier one here. Because if I'm thinking about the horizontal line segment, that's going to be washer method. Like rotating that around the axis will give me a washer. I need to integrate, I need to solve this function for x. It's x equals arc sine y will be this part, the left half of the hump. The other half of the hump will be x equals pi over 2 minus arc sine y. Or no, it's pi minus, right? Yeah. For the right half of the hump. So those are the two things that I need to subtract to get the r squareds. So it's going to be the integral I need to let x go from 0 to 1. Of, what am I integrating? Big R squared, pi times big R squared minus little r squared. My big radius is the distance from pi minus sine inverse y to negative 1. So that'll be pi minus sine inverse x minus 1. This is not an integral dx, it's an integral dy. That's what's wrong here. The inner radius will just be arc sine y minus 1. I guess I'll write that in green to match the other one. And yeah, I don't want to integrate that one. This is squared and this is squared. There's the integral set up for the washer method. For the shell method, I'm picturing a vertical line segment. It is much easier to take the distance of this vertical line segment. We're going to integrate. Our x value needs to go from 0 to pi to catch all of those vertical line segments. It's going to be 2 pi. The radius is the distance from our x value to negative 1. So our radius is x minus negative 1. And our height is just sine x. That seems way easier to do. Let's do that one. I want to do this by parts, I guess. I want to let u be x plus 1, du will be 1, dx, dv will be sine x. So v is the integral of sine x is negative cosine x. This has the dx, you don't have a dx. So I get 2 pi times uv, x plus 1, negative cosine x evaluated from 0 to pi, minus the integral of v du from 0 to pi. V du is negative cosine x dx, and you still have the 2 pi on you from the constant out front. Plug in pi. I get negative 2 pi, pi plus 1. Cosine pi is negative 1. Minus, now plug in 0, negative 2 pi, 0 plus 1 is 1, times cosine 1 is 1, 1. Plus 2 pi, integral of cosine x is sine x. I need to evaluate sine x from 0 to pi. Oh, that's 0. Sine equals 0 at both 0 and pi. So this is the whole answer. 2 pi squared plus 2 pi plus another 2 pi, I'm getting 2 pi squared plus 4 pi. Cool. Midpoint rule junk. We're using all three to approximate the integral of 1 over x squared, first with delta x equals 0.25, then with delta x equals 0.1. For each of these, we need to find a bound on the error. All right. So, our interval is 1 to 2. We're cutting it into 4 pieces. So that'll be 1.5, and that'll be 1.75. And this will be 1.25. For the midpoint rule, we're going to get the integral from 1 to 2, 1 over x squared dx is about, I need the midpoint of each of these intervals. So I need to take 1.125. I need to take 1.375. I need to take halfway between here and here is 1.625. Halfway between here and here is 1.875. I need to plug those all into the function, raise them to the negative 2. For the midpoint rule, you just add them all up. Adding them all up and dividing by 4 would be an average. Multiply that by the length of the interval to turn that into an integral. The length of the interval is 1, so this is just an average on all of these. The error on the midpoint rule is at most where do I have the error formulas written down easy to reach? The error for the midpoint rule is at most the length of the interval cubed maximum of the second derivative over 24 n squared. Our n value is here 4. How big is the second derivative? Our function is x to the negative 2, its derivative is negative 2 x to the negative 3, so the second derivative is positive 6 x to the negative 4. If I evaluate, I'm going to need the third and fourth derivatives in a second too. I might as well do those. Negative 24x to the negative 5. Fourth derivative is positive 120 x to the negative 6. X to the negative 2 is decreasing after 1. X to the negative 4 is also, it's at its biggest at 1, so the biggest value of the second derivative is 6. I get 1 times 6 over 24 times 16. This is 1 over 64. This will be accurate up, give or take, at most 1 over 64. I'm not going to stick this in my calculator and get digits on it, but it's worth doing it and comparing it with the real value. There's the midpoint rule. Let's try the trapezoid rule. The integral from 1 to 2 of 1 over x squared dx will be about. The trapezoid rule uses the left and endpoints. So it'll be 1 times the left endpoint, 1 to the negative 2, plus 2 times the next one, 1.25 to the negative 2, 2 times the next one, 1.5 to the negative 2, 2 times 1.75 to the negative 2, 1 times 1 to the negative 2. I want the length of the interval times an average. We're adding up 2, 4, 6, 7, 8 points, so I want to divide by 8 to turn that into an average. There's our estimate for the trapezoid rule. The error on the trapezoid rule is the same as the midpoint error, but with a 12 instead of a 24. I have that right? I do have that right. Will be 1 times 6 over 12 times 16. So it's the same thing, but double will end up being 1 over 32. For Simpson's rule, I'm going to use these same 1, 2, 3, 4, 5 points. So, like I gave the instructions to make it clear. What does delta x equals 0.25 for Simpson's rule is, I think, vague. I'm making it more specific, saying use 4 or 5 points. That's easy to understand. I'm using these 5 points. It should be 1, 4, 2, 4, 1. It's the same as the trapezoid rule approximation. 4 times 1.25 to the negative 2. 2 times 1.5 to the negative 2. 4 times 1.75 to the negative 2. 1 times 1 to the negative 2. I want the length of the interval times an average. To make this an average, divide by 12. The integral is about that. The error on Simpson's rule is going to be at most b minus a to the 5th k4 over 180 times 2n to the 4th. Length of the interval is 1. K4 is here. This function's at most as big as 120 over 180 times 2n is here. 1, 2, 3. Like we had 4 intervals, so 2n is 4 to the 4th. How much do you reduce? 120 over 180 is 2/3. So 3 times 128 is 384. That one is way more accurate. That was using delta x equals 0.25. Let's do it now with delta x equals 0.1. For the midpoint rule, I want to take the midpoints of each of these intervals. It will be 1.05, 1.15, 1.25, 1.35, 1.45, 1.55, 1.65, 1.75, 1.85, 1.95. I want to scale it by something. I want to remember that it's the length of the interval times an average. We added up 10 points, so I need to divide by 10. Turn that into an average. The error on the midpoint is at most b minus a cubed k2 over 24n squared. All of this is the same except for the n value is now up to 10. So that's going to improve our error. This is 6. 24 times 100. This is 1 over 400. We're off by at most 0.0025. I think that's right. The trapezoid rule. The integral from 1 to 2 of 1 over x squared dx should be about, I want 1 of 1 to the negative 2, 2 of 1.1 to the negative 2, 2 of 1.2 to the negative 2, 2 of 1.3 to the negative 2, 2 of 1.4 to the negative 2, 2 of 1.5 to the negative 2, 2 of 1.6 to the negative 2, 2 of 1.7 to the negative 2, 2 times 1.8 to the negative 2, 2 times 1.9 to the negative 2, and 1 of 2 to the negative 2. Those are 20 numbers we added up, so to turn that into an average, we divide by 20, multiply that by the length of the interval. There's our estimate. The error on the trapezoid rule is at most, it's double the error of the midpoint rule. b minus a cubed k2 over 12n squared will be 1 over 200 for this one. And for Simpson's rule, the integral from 1 to 2 1 over x squared dx should be about, it's this with a different scaling. 1 to the negative 2, 4 times 1.1 to the negative 2, 2 times 1.2 to the negative 2, 4 times 1.3 to the negative 2, 2 times 1.4 to the negative 2, 4 times 1.5 to the negative 2, 2 times 1.6 to the negative 2, 4 times 1.7 to the negative 2, 2 times 1.8 to the negative 2, 4 times 1.9 to the negative 2, 1 times 2 to the negative 2. How many points did we add up? 1, 5, 7, 8, 9, 10, 11, 12, 13, 17, 19, 23, 25, 29, 30 points. So divide by 30 to make it an average, multiply by the length of the integral to make it an integral. Length of the interval to make it an integral. And the error on Simpson's rule is at most b minus a to the 5th k4 over 180 times 2n to the 4th. Here that's 1 times k4 was 120 over 180. 2n is now 10 to the 4th. So this is 2/3. 10 to the 4th, that's 4 zeros on that. Oh, I guess that reduces now. This is 1 over 15,000. It's a nice example for showing off how Simpson's rule is way more accurate. It is crazy how accurate Simpson's rule is. Okay. That's it. I'm going to stop streaming. Before I post this, I'm going to try and do that integral. Cool. Video end.